Okay, so thank you very much for having me and allowing me to present this work. So this is part of the task 4 of the climate change project, which is the application testbed. And it's actually only one part of that, so there's actually a number of teams that have been working on this, and Graham Greene presented a bit more broadly on the whole project yesterday. Today I'll be focusing on the University of Adelaide contribution to that, and so I'd like to acknowledge my co-authors there, but also acknowledge, I guess, the Goyder Institute more generally for the support, as well as the interactions with a whole range of other people, particularly Steve Charles for providing a lot of the downscale projections. So it's been quite a big job. It's a job that, I guess, it's been about an application testbed. So it's been an opportunity to really think about how do we use these downscale projections of rainfall and other atmospheric variables to come up with some useful end products in terms of projections for runoff. And so it's really been about sort of exploring that process rather than about making very specific projections. And so this presentation today will give you a little bit of a sense of the projections which were already covered yesterday, but also talk about some of the issues that we've come up against in terms of what it means to look at future climate change. Many of you will have already seen this slide here. So this is the catchment that we've been looking at for the application. It's the Onkaparinga catchment. And we really divided the catchment into 3 sub-catchments, which comprise the majority of the flows that go into Happy Valley Reservoir and are available for Adelaide's water supply. The first one is the Holgrave Weir catchment, which is the big red catchment there, which basically flows into Mount Bold Reservoir. There was a smaller catchment at Chunga Creek catchment, which we looked at as well, that also flows into that reservoir, and then Scott Creek catchment, which is downstream of the reservoir, but also makes up some of the surface water supply. The reason we chose those and discretized the catchment in that way was really based on data quality and the availability of long streamflow gauges that we were able to trust. There was a lot of other streamflow gauges that were short or had issues that we sort of identified over the course of the project, and so this is the reason why we chose those there. Then we analysed a very large number of data. So 2 RCPs, 15 GCMs, as Steve Charles mentioned, and then 100 statistically downscaled simulations, each being something like 100 years of daily time series data. We put them into 4 hydrological models, and I'll talk about that later, and then looked at them separately for 3 subcatchments. So at some point I calculated there was something like 50 billion different calculations that were needed to produce these results or something like that. It's a huge volume of data. One thing we didn't do in this project was actually just look at the sort of the best 6 models that Steve Charles mentioned. The reason was that we didn't really have access to what those were at the time that we were able to do, or we had to do the simulations, because the final thing was due in June last year. So we ended up doing the projections across the full ensemble of 15 climate models. One of the assumptions that's inherent in just about pretty much in every model, is this assumption that the relationships embedded in that model are stable over time. And this is an assumption that we call stationarity. And there was a fairly prominent paper about a bit less than 10 years ago in Science that proclaimed stationarity as dead. Because we have a changing climate, we're changing a lot of the forcings, the atmospheric forcings that act upon a catchment. We actually cannot trust this assumption of stationarity anymore. So what do we mean by stationarity? So this was the first thing that we really spoke about. Basically, if you have a conceptual model of some sort, let's say there's a relationship between rainfall and runoff. So this is what I'm drawing here is just a straight line. This is just a conceptual model, it's not reality. But we're assuming that there is some sort of relationship between these variables that we can capture through a model, which will allow us to say if we get rainfall of this much in a given year, we can estimate what the runoff is likely to be. Now, one of the problems that we have is that relationship might not be stable. Actually, let me just talk about climate change first before I go there. The assumption under climate change is if we know the change in rainfall, that we can also understand the change in runoff. And that's really given by, say, going from that green curve to the red curve there, where we have a decrease in rainfall. And so, as I was saying, one of the problems that we might have is what happens if that relationship itself changes over time. And this is what we call non-stationarity, because we can't assume that rainfall runoff relationship is stable over time. And yet that assumption is inherent in a lot of hydrological models. And so the question is, well, what do we do about that? And unfortunately, I can't say that we completely solved that problem, but we came up with some ideas of how to start tackling this issue. And so we developed and published a strategy for dealing with non-stationarity in hydrological models. Now, one thing just to point out, which is a little bit esoteric, but I guess sort of comes to the heart of the problem, is if you have a true model, so a model that reflects reality completely, then there is no non-stationarity. So, everything obeys the laws of physics, and those laws essentially will stay immutable over time. And so the reason that non-stationarity rises is because of the inherent simplifications and the fact that we're leaving out processes in the model. So, say these relationships here can change over time because we have catchment development, urban development in a catchment that change the relationships, and those are not in the model, and therefore we get these sort of apparent, these changes. So as soon as we start incorporating some of these processes into the model, we can actually come back to having stable relationships within the model. So what we did in terms of developing this strategy is the first thing to rule out is that there might be systematic errors in the data that might be causing some of these changes through time, or apparent changes through time. For example, there's stream gauges that are known over time to change in terms of the rating curves. You have changes to the vegetation around the gauging and so on. And that can cause the appearance of changes in time, which is not actually a genuine result. And same if you move rainfall gauges and so on. So the first part is just to rule out some of these issues. And we actually did a huge amount of work, which I don't have time to present today, that was looking at trying to understand uncertainty in the data, the quality of the measurements and so on, and try to eliminate, as best we could, sort of spurious causes of this non-stationarity. The second thing is to then say, okay, if we do detect this non-stationarity, hypothesizing a set of hydrological model parameterizations that can kind of address this. And I'll cover that in a little bit. And then it comes around to trialing some of these alternatives, and then figuring out a way to actually select a subset that we think performs reasonably well. Now again, this really challenges a lot of conventional hydrological modelling thinking, because in the past we tend to think in hydrological models, let's just assess it against the historical climate. We don't really have benchmarks to say which ones are actually better in the context of can it deal with future change. So for the hydrologists in the audience, you'll be familiar with, say, Nash-Sutcliffe as sort of a measure of how good a hydrological model is. That doesn't really tell you if the model captures the right processes that are changing in time. So we did that, and one thing we did is we looked at allowing some of the parameterizations in the hydrological model to change over time. So we used a model called GR4J, which is a very simple 4-parameter model. And the way it works is it has a couple of buckets, what we call buckets, which are sort of conceptual stores of water in a catchment. And so rainfall can come into those buckets and essentially fill them up, and then eventually they empty out as stream flow. And so part of the calibration of those models is really working out how those buckets configured, how big are they, which affects how the storage, I guess how the rainfall gets converted into runoff, or evaporation, or sometimes groundwater fluxes as well. And what we found was that in a traditional GR4J model, the buckets have to stay the same size. And so, you might get different amounts of water in the bucket from one day to the next, but the actual size of the store should be constant. And what we found was if we allowed them to vary and calibrated them in a way that allowed them to vary, we actually found that the bucket wanted to really increase during summer and decrease during winter. And so that's the sinusoidal sort of looking variation that you see in that figure. And so what that meant was that it thought that the model was too responsive to rainfall in summer, so it actually wanted to increase the size of the bucket so it looked like, so that rainfall had less of an effect to runoff. And then it was not responsive enough in winter, so it wanted to decrease the size of the bucket so it actually caused more rainfall to be converted to runoff during winter. So it actually sort of found that there was some structural weakness in the model itself that by changing the parameterization, it allowed it to sort of compensate for that to some degree. The other thing that we found was a systematic trend, and these are two different versions of this non-stationarity. So what I'm really referring to is this upper line, the dotted line there. You see that kind of increasing trend. So the buckets seem to want to increase, which means that there's more storage, which basically means that the catchment seems to have become less responsive to runoff over time. So in fact, for amount of rainfall, you get less runoff over time and more going to evapotranspiration. And so there's a range of different reasons for why that might be. It could be changes to the catchment, farm dams and so on that weren't explicitly parameterized in the model, keeping in mind that we used a very simple conceptual model here. It could be changes in vegetation dynamics, irrigation, groundwater extraction. There's a whole range of different plausible explanations. And unfortunately, we couldn't come to a single one because of data limitations and the fact that there's multiple competing hypotheses that are very hard to rule out. So we made some assumptions and finally looked at some different models. And I won't go into all the details here, but we sort of compared about, I think it's 22 models from memory, using different metrics, and we sort of grouped them in a few different classes. Ones that really captured the sinusoidal variation from year to year, some that kind of captured that trend and assumed that that trend would sort of stop around the 2000s when we know that there haven't been much more development in terms of farm dams in the catchment that we were looking at. And so we ended up selecting an ensemble of 4 models that captured different assumptions around this concept. So I guess that's a bit of a whirlwind sort of explanation of what's really been quite a few years of research around the method development. It's really sort of just summarising in a few words kind of a fairly sort of complex set of problems that we're trying to address there. Once we had that, we then applied the model to the downscaled rainfall and had a look at how well it did in the historical climate. And what we found was that the model tended to underestimate a little bit the average annual runoff, and a lot of that was basically because of the extremes. So the extremes in the downscaled rainfall data seemed to be a bit below what we actually observed in the past, and that then led to a bit of an underestimation. But that doesn't concern me too well. The extremes worry me a little bit, and I'll get back to that. But the slight biases don't worry me too much in the context of the projections because we've really looked at changes between historical and future. So once we've kind of come up with a baseline, everything is relative to the model world baseline. So just quickly going to the projections, these projections were covered in a fair bit of depth yesterday, so you would have seen most of these before. But essentially these are sort of exceedance probability curves or cumulative distribution functions that showed the range of projections in mean annual streamflow change relative to the baseline, which we selected was from 76 to 2005, and that's plotted for all the different time slices. So if you look at, say, the 36 to 65, so it's centred on 2050, we sort of on average expect, say, a 25% decrease, but there is a sort of a tail end probability that you could get as much as 40 or more % decrease by that sort of 2050 window. And of course, as you get further into the future, the declines get greater. A lot of this, and the fundamental issue with South Australia and a lot of the South Australian climate is that it's very sensitive to small changes in rainfall. So we tend to get elasticities of 2.5, sometimes even more, up to 3, which basically means that a 10% change in rainfall leads to a 30% change reduction, or 25 to 30% reduction in streamflow. And so that's really critical because you don't actually need to change the rainfall that much to have a huge impact on runoff. And that's actually consistent both with historical data, just looking at dry years and wet years, and what the model's projecting will happen in the future. Most of our uncertainty was ultimately based on GCMs and the climate model uncertainty. So as Steve Charles sort of alluded to, we might be able to reduce it a little bit by only selecting a subset, but of course there's always a risk when you're selecting a subset that you leave out a model that happens to capture some processes. So I wouldn't have thought that you end up reducing it by all that much if you start looking at subsets. In contrast, the hydrological models didn't really, we had those 4 models with different assumptions, and it didn't really lead to a huge amount of the overall uncertainty. In the near term, so these are PDFs, overlapping PDFs here for the 2 RCPs that we looked at, 4.5, which is really a low-end emissions, and 8.5, which is tracking on the higher end. So this is what we're tracking on at the moment. And these PDFs sort of overlap for these 2 in the near term, but as you get further out to the sort of end of century, or from mid-century to end of century, they start really splitting. And so by the end of century, the expected change is something like 25% for an optimistic scenario, down to 50% decrease for the more pessimistic scenario. So in any case, there seems to be a decrease, but there does seem to be a split in terms of projections based on RCPs as you're getting further into the future. And then finally, low flows seem to be more sensitive than average flows, so the dry years seem to be drying out more than the wet years. And the peak daily flows are a bit less sensitive, so we seem to see less change in terms of the real high flows compared to the low flows. Now, just one quick caveat on this. This is not about flooding, so we didn't do any analysis looking at really the extremes and what might happen to flooding, and I would sort of argue that the models, the hydrological model, is not really set up for looking at flood risks. So this is sort of, I guess, the 99th percentile daily flow, which happens 3 or 4 times a year. It's not a flood flow that we were looking at. So I guess that sort of leads to the areas where we still probably need to really think a bit more carefully. One is around the flooding, and that's something that we haven't addressed very much in this project, but it's being addressed in some other projects outside of Goyder that sort of looking at national flood risk. And then also long-term change in natural catchments, which is really looking at, are there vegetation changes that, how does vegetation respond to, changes in temperature, and what does that mean for the rainfall-runoff relationship in the future? So that's really all I wanted to say. Basically, the key messages is a substantial decline in mean stream flow expected based on these results. They're largely due to just the nature of the catchments in South Australia and the fact that they're very sensitive, and that there is still a lot of uncertainty, a lot of it due to GCMs and also because of climate change, greenhouse gas concentration pathways moving into the future. So thank you very much.